The shaft shown is made from a steel tube, which is bonded to a brass core. If the torque of 250 foot-pounds is applied to the end, what's the maximum and minimum shear in each material? So now as we look at this, I have this brass core that is bonded to the steel shaft, and I'm applying a 250 foot-pound torque to it. And so the question is, okay, well, what is the maximum and minimum shear stress? And so how do I solve that? Well, I have an equation that tells me that my shear stress is the torque, whatever radius that I'm looking at, over J. The biggest problem with this is you immediately go, oh, well, there's 250 foot-pounds of torque on this combined shaft. So that means there's 250 foot-pounds of torque in the brass and 250 foot-pounds of torque in the steel. Well, that's not true, because we have, if you look at it, because you want to find the internal torques, that's what's applied at the end. Well, if I do a free body diagram, I do have 250 foot-pounds that's being opposed at the wall total, but we have some torque in the brass and some torque in the steel, because each of these materials is going to carry a bit of the torque that's being applied to both of them. So as we look at this, we have to sit there and figure out, okay, well, how much torque is in each one? So as I look at this, I've got, I'm applying the 250 foot-pounds in the positive direction. Let's do a sum of moments. Let's say the counterclockwise is positive. So as I look at this, I have 250 foot-pounds of torque. Now I'm going to want to convert this over into inches. The reason I do is I look at my modulus of rigidities are in inches. So we're going to sit there and go, okay, well, there's 12 inches in 1 foot. So we'll convert that over to be in pound inches instead of pound feet, or inch pounds instead of foot pounds. And so then I have my steel and my brass are working in the negative direction. So minus steel minus the brass. And if I get this all rearranged here, the torque in the brass plus the torque in the steel is going to have to equal all of this. And so what you'll get there is 3,000 inch-pounds, or 3 kips times inch. So we look at this, and what does that tell us? Well, it's statically indeterminate. So we're not going to be able to figure this out by statics alone. And we need to know what those torques are so we can calculate out what those we need to know what those internal torques are so we can calculate out what our shear stresses are. So since this is statically indeterminate, we have to come up with some kind of compatibility equation. So as I look at this, what's going on is, unlike other problems that we've done where it's been grounded at both sides and we've been able to say, well, the angle of twist from point A to point B is the same because they're grounded, we don't have that. But we do know that the angle of twist have to be the same because they're bonded together. So my angle of twist has to be the angle of twist in the steel, which all has to be the angle of twist in the brass. And so this is where we're going to be able to use that relationship. And that was not some weird glitch. I accidentally overlaid another picture on top, and so we don't want to do that. So what we're going to do is we're going to exploit that relationship. So the angle of twist in the brass has to equal the angle of twist in the steel. So TL over JG of the brass is going to equal TL over JG of the steel. Now, it's 4 feet long. Both the brass and the steel are 4 feet. So what can I do? Well, I can divide through by 4 feet. So those links are going to cancel out. They're the exact same. Material is not the same, but we've been given those material properties. J's are different. So we're going to have to calculate those out too. So let's do that first. So the J brass, still circular shaft. So pi over 2 r to the 4th. So pi over 2. And if I look, that brass was a 1/2 inch radius, because the picture shows in radius, not diameters. So 1/2 inch, I'm going to raise that to the 4th to calculate out what our, and that gives us 98.125 e to the negative 3 inches to the 4th. So we're going to need to do the same thing for the steel. Steel is a little bit different because, once again, we're going to end up with a donut because we can't take the material from the inside. We have to pull that out to get our J's. And actually, the J of the inside is the exact same as the J of brass. So what we can do is sit here and go, okay, well, I'm just going to do the outer radius of my thing, and I'm going to subtract from it the J of brass, which is the same thing as just subtracting the inner radius of everything. So pi over 2, r to the 4th, that's 1 inch, raised to the 4th, minus 98.125 e to the negative 3 inches to the 4th is going to give us 1.472 inches to the 4th. Because this mess over here is just basically pi over 2, so 1.53 minus 98.125 times 10 to the negative 3rd. So there's our two J values. So now we'll just plug them into the equation. So what do I have? Well, the torque of the brass will just be torque of brass. We don't have the length because we canceled that out. The J of the brass is 98.125 e to the negative 3 inches to the 4th. I'm going to multiply that by the G of brass. So if we go back and look at the equation, it tells us it's 5.2 times 10 to the 3rd KSI. So 5.2 times 10 to the 6th PSI. And that has to equal the torque in the steel. J of the steel is 1.472 inches to the 4th. And then our G of steel is 11.4 times 10 to the 3rd KSI, or 11.4 times 10 to the 6th PSI. So at this point, when we take a look at these things and kind of move things around, we can say, well, the torque of the steel is going to be 32.88 times the torque in the brass. So the steel is carrying much more of our torque than the brass is. So if I look at that and I go back to what was my equation that I wrote down on the other page, we'll go back here and go back to our statically indeterminate equation, that the torque in the steel plus the torque in the brass is 3 kips times inch, or 3,000 pound-inches. So if we do that, we put those two together, torque of the steel is going to be 2911.5 pound-inches. And then the torque of the brass is going to be 88.5 pound-inch. So, boxing it, it's not the answer, because it's only part of it, because we have to go to the stresses. I'm just boxing that so we can see it. Just so you know, that's works out to be the steel is 242.6 foot-pounds. The brass is 7.38 foot-pounds. Not a small difference between those two. The steel's carrying much more. So now we get to, okay, well, now I have to take a look at things, and I calculate out my shear stress. Shear stress is T rho over J. What is my maximum shear stress? It's going to be at the biggest diameter. It's going to be the biggest radius. What's my minimum? It's going to be the smallest. So it's really easy starting out. One of the minimum of brass. Now the minimum of brass is going to be 0 psi. It's right at the center. There is no radius. That's going to be the minimum. Neutral axis, all that great stuff. So now let's look at the maximum of the brass. So the brass maximum is going to be the torque in the brass, which is 88.5 pound-inches, times the radius, 0.5 inch radius, divided by our polar moment of inertia. I know we already calculated it out. I'm just going to write it out again. 0.05 raised to the 4th times pi over 2. So the maximum the maximum stress in the brass is 451 psi. Okay, so now let's take a look at the steel. We have to actually worry about the minimum steel. It's not just 0 because it is at the same spot as the maximum for the brass. But since the material is different, we're going to have different answers. So the minimum in the steel is not 451 because the steel is taking on so much more of the torque load, but it's the same radius. But it's also a different polar moment of inertia because it's a different geometry shape. So 1 inch to the fourth minus 0.5 inches raised to the fourth times pi over 2. We bash all that out, and it's 989 psi. So even though it's at the same location, it's a much higher stress. So finally, we have our maximum stress. And the maximum stress in the steel, where does that happen? That happens at the outside radius. It's our biggest radius that we can have. So 2911.5 pound-inches times 0.5, times 1 inch. And then we're going to take that, we're going to divide it by the same polar moment of inertia. We take the polar moment of inertia of the outside one, we subtract what's going away in the middle, and then we're left with 1977 psi. So that's the maximum shear stress that we have. So obviously the shear stress gets bigger the closer we get to the edge. And actually here's that picture that popped up before. And this is how the shear stress is distributed between those two materials. Starts at 0, neutral axis, 0 radius. Come out to 1, 451 in the brass, 989 in the steel. Goes up to almost 2000 psi in the steel.